Okay, I think you can see now my screen. Okay, so the agenda of this webinar is below. So you will have three parts. Into the first part, uh, you will see all the presentation about the multiphysics and topology optimization that some user have been present during Japan uh, user conference. The second part will be about the presentation made on the automotive application. And the last topic is about the aerospace application. So we will present you some, we will show some presentation on the aerospace application using JMAC. Okay, sorry. Okay, so let me start with the multiphysics and topology uh, optimization. So in this first part, so I will show you some application done by some user. So the first multiphysics application is the noise vibration into induction motor using JMIC. So this presentation was done by Emin Amar, so the Dr. Emin Amar from Jomon Electric. So I will not follow all the slide in detail. So what I will do, I will just give you some main information of this presentation. So yeah. So Jemong, not that Jemong, it is the manufacturer of power electric rotating machine since 18 1898. So Jumon, it is a part of Altawest Group since 2007. Yeah, Jumon have 600 employees in the world. This is the cell made by Jumon. In France, so Jumon have 4 sites for manufacturing site in France and one in India. So this is the market area of Jemong. Here, here this is one product of that made by Jemong. So you have synchronous generator. So here you have some turbo generator, and here you have some high diesel generator. Yeah. So this is another product made by Jemong. This is the product. So, so I will go to the case study. So here, so to make to study the noise into the ignition motor. So here you have the data. So the specification of the motor used for the simulation. And the problem is that with this motor, you must see that there is some abnormal noise and vibration. So you have some more than 100 decibel for sound. So this is not good for the working of the motor. So this is why Jumbo make this analysis, and here you have the 3 causes of the vibration. Yeah, so they have seen that this higher noise can be due to 3 causes. So the first one is the eccentricity effect of the rotor, and the second one is the break-on bar inside from the squelette cage of the rotor, and also the resonance of the motor structure resonance of the motor. Okay, so after making some some vibration measurements, so the velocity spectrum, and they have seen that there is some possible source of the noise and vibration, so around 140 Hz here. So maybe this can be the cause of this higher noise. So they also try to make the same spectrum measurement into the into the case where there's some eccentricity into the rotor, and they see that the eccentricity the eccentricity cannot be the cause of the high noise. Yeah. So this is why here they will try to to focus on the structural resonance by making some noise vibration calculation based on the automatic force extension. So they will focus on the automatic force extension. Yeah. And here, this is some equation to calculate the radial forces. Yeah. And here, this is the different investigation plan that they follow. So in the first step, they make some electromagnetic analysis in order to get with more accuracy the electromagnetic forces, and then they will try to compare with the test result. In the second step, they will try to make some structural analysis. So the eigenmode analysis that they will compare with another software. So into this second step, they will try to get the again vibration mode. Yeah. Into the third step, they will try to make some acoustic analysis. And to finish, they will try to find how to reduce this noise into this motor. So here, this is some setting that they made into JMAC. So we have some information about the shape that they use, and also the mesh. This is some circuit setting. Yeah. And here, this is some result that they got into JMAC. You have the no load voltage, and you have the full load voltage compared to the test. So the red one is the measurement test, and the blue one is the JMAC result. So you see that the JMAC result is matching well with the test. And they also try to calculate the torque using some option, some advanced option into a JMAC. So the TPEEC option that you have into JMAC, and they say that without using this TPEEC, the convergence of the torque is the time to reach the convergence is very high than the case that we use the option. So here is that with the TPEEC, we can reduce the time to reach the steady state. So we will, with the CPC, we will reach quickly the steady state. Yeah. See. So after running the electromagnetic analysis, so then here they have extract the Maxwell radial force here that you can see here. Then after applying the 3D, the FFT into this 3D graphic, then they got this one, and here they see that there is some noise electromagnetic sources that they select to make the acoustic um, analysis. Here, this is the structural model here. So based on the 2D analysis, they have used this option, extend model to 3D, in order to create the 3D model of the stator. And here you can also see the mesh and the number of mesh element. So here, this is some eigenmode vibration. So this is the eigenmode result, and that you can see here with different frequency mode here, and here they can see that here with the eigenmode number 4, you can see that here they have compared the ANSYS, the eigenmode calculated by ANSYS and the eigenmode calculated by GEMAC, and you can see that GEMAC is matching well with the electromatic with the frequency calculated from the analytical formula. So this is the process to make the sound vibration analysis. So here they have combined the force calculation analysis with the eigenmode calculation to then they will combine these two to make a real vibration noise analysis. And here you can see some setting that they have made in order to make this analysis. So here you have the damping factor that they have used. Okay, so this is the sound pressure level result that they got into GEMAC here. So the objective here is that they want to reproduce the test condition here. And here they have measured, they have also display the sound pressure level depending on the frequency. So to reduce the noise, the noises, they have tried to analyze two aspects. The first one is the modification of the stator, and here this is the natural frequency of the stator. So if so to modify this frequency, we need to modify the stator shape. So we can modify we can find the new stacked length, or you can find also the new winding distribution. The second aspect that they want to modify in order to reduce the noises is the rotor shape here. So here they try to make different model here with different rotor bar and also different number of pole here. So here for each model, they run some simulation here compared to the original model here. So they see that with the model 2, the current is very higher, and also the torque is 14 is more than 40 times the reference shape, the reference model. Yeah, and this that the design tree is more is matching the result of the design of the model tree is around is approximately the same with the original one. So they try to make the NVH into the model tree, in order to see if the noise is lower than the original cases, than the original model. And here, this is, you have the distribution of the radial force of the FFT of the radial forces here. And here you have the sun pressure level of the original model, so the design 1 and the design 3 here, and compare to the problem that they found initially. So they see that they have seen that with the model 3, the noise is more reduced. Okay, so in the conclusion, they have said that using GEMAC, GEMA have been able to investigate the origin of the electromagnetic noise, and then they have also find rapidly the solution with the low cost. Yeah. And in the future, they see that they will use GEMAC at the early stage of the machine design by coupling GEMAC with some analytical software. Okay. Into the second presentation about the thermal analysis into the vehicle motors. So here I will show you some work made by some engineer of Toda Racing on the coupling between GEMAC and some CFD tool in order to analyze the thermal behavior of the motor. So here, this is some information about the Toda Racing company. So Toda Racing company have different business components. So here, for example, they make some development and manufacturing of some racing part and racing engine. They also develop and produce some automotive part. So you have a lot of other besides that Toda Racing made. So Toda Racing is a Japan company. So it's based I think in Tokyo. This is the different product of Toda Racing. Okay. So this is also another automotive component that they manufacture, that they develop and manufacture. Okay, so let me go to the case study. So we know that we know that the safety calculation is very important for the motor design because, for example, the CFD Toda have tried to set up to run some thermal fluid flow analysis by combining GEMAC and SF flow in order to simulate the cooling, the fluid cooling into the motors. So here, here you have the two products that they have used. So you have GEMAC and you have SF flow. So here we have SF flow of Cradle. Yeah. Okay, so to make this study case, so they divide it into 3 phases. The first phase where they will use some sample models, some sample geometry in order to understand the process to calculate the heat generation into GEMAC and to see how this can be import into the SFlow in order to evaluate the temperature. They have also tried to confirm this coupling by using another safety sulfide. So that's the same place. So in the second phase here, so after understanding the process to make the coupling between GMAC and SFlow, then here they have tried to make coupling using the real model here. So using the real model, they have tried to model all the shape of the real shape of the real model. So they try to build the shape of the stator, rotor, and so on. And they have also make some investigation and also make some automation according to the detail and result. Into the last phase, they have tried to make some comparison between the actual production and also between the GMAC model with the testing. Okay, so here you have the coupling process. Here you have the process that they follow to make 2D and 3D model into GMAC. So they make a 2D static and transient magnetic calculation, and also 3D magnetic field combined with iron losses in order to calculate the copper losses from the winding, and also the iron loss from the core of the motor, so rotor and stator core, and also the master loss. Yeah. Then this loss will be exported to a specific format that can be read by SFlow using the multipurpose file export tool of GMAC here. So here into the SFlow, then they will try to rate this losses as the heat condition here, and based on the CAD format here, they will try to make some thermal fluid analysis. Here they will define a material, some load heat generation, and here they will also try to make some thermal analysis into GMAC, and then they will make the comparison. The thermal analysis here, they will try to use the final model in order to make some optimization, and then they will try to redo the same test to validate the thermal behavior of the final model. So this is the sample model and the actual model that they use. This is the real model, the picture of the real model here, and also the distribution of the wire from the winding for the coil. Okay. Let me go to the GMAC result. Sorry. 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 Okay, so maybe there's no detail about the GMAC result. What I will say here is that yeah, so they make some analysis into GMAC, and they also use some another tool of Hexagon. So here you have Cradle for thermal analysis, and also Romax for noise analysis. And they have tried to make some correlation between all this simulation, you know, and the test in order to find in order to improve the performance of the motors. Yeah, I think that's it for Toda racing. And the next presentation is about the topology optimization. Yeah. So here I will show how Hitachi have used the topology optimization of JMake in order to find some new shape of the motor. So this presentation was done during the user conference in Japan, and it was done by Yukihiro Yoshida, which is one engineer of Hitachi Automotive. Okay, so I will not go in, I will not follow all the PPT, but I will just give you some information about this presentation. So Hitachi, it is a Japan automotive company. So they've also developed and manufacture some automotive component, some industrial machine, and some other systems. So this company is also based on Japan, and this is the revenue of Hitachi automotive system. And here you have in the world, here you have all the location of Hitachi in the world. So here, this is the different business area of Hitachi automotive system. So in order to resolve some customer request, so about the miniaturization of the motor, the reduction of the loss, to get more or higher output power or output torque, and to reduce the price, yeah, to reduce some demonstration effect. So they have made some topology optimization into JMake. So they need to make some topology optimization into JMake. So for that, they have used two type of model. So here you have the sample model of motor with sample magnet shape, and here you have the second one with the V shape of magnet. And here, this is the process that they have followed in order to find the new motor shape. Yeah. Okay, so here you have different another different model here that they also want to use and into JMake. So they will use the topology optimization feature, which have two methods or two solvers. So you have the advanced solver based on the normalized Gaussian network method, and you also have and you also have another another topology optimization solver that they will not use, that they have not used for this model. Okay, here you can see some result, some generation result that they have run. Okay, so here, this is the first model. This is the discretization of the Gaussian. This is the discretization of the design region that they have made using the Gaussian function. You have around 1885 Gaussian function. Here, this is the objective function that they have applied into JMake, and also some constraint here. And they've defined this based on the NT curve, on some point of the NT curve of the motors. And they have also make some calculation to measure the simulation time, and they have seen that uh, they have that with using the PSL, so the power simulation license, they have been able to speed up the calculation. So they have run it into eight days. Yeah. They have also seen that using some JMAC option. So JMAC, there's some 2D property option like the incomplete Koleski conjugate gradient. They have seen that they can also reduce the simulation time if they use the direct method to improve the linear, to improve the calculation of the linear equation into the analysis. Here you have some result of the topology optimization of the flux barrier into the rotors. Here you have the scatter plot of the extension force of the 48 harmonic orders. Yeah. Here you have the Pareto solution compared to the current model, so the actual model here. And here you can see the optimal solution is into the Pareto curve, one, and you can confirm the shape here. So here they have also made some sensitivity analysis into the original model. So here you can see the area where they have made the sensitivity analysis in order to reduce the effect of induced voltage, and also reduce the torque repel of the model of the motors. Into the second step, into the second to the case, they are also try to combine some multiple study in order to make some multi-physics optimization. So this is the this is the reference model. Here now, this is the design region here, and this is also some region that they want to see if it is possible to maintain, so to define as a magnet. Yeah. And here you have the state that they some condition that they have take into account for this analysis. Okay, so this is the process that they have follow for the topology optimization. So they have combined these two analysis with this condition. So for the topology optimization, and after making this, they will extract the final model, where they will try to apply the classical optimization. So they will try to define some dimension, and then they will follow the same process than this in order to optimize the dimension. Yeah. Okay, so here is also the model with the different magnet angle. So it's the bishop magnet with different angle. So here you have the distribution of the Gaussian function for the different magnet angle here. and they have defined some objective function and constraint based on the entry curve of the motors. Here you have the different results that they have obtained for different magnetic angle, and they have seen that for the first three model, the torque is very small than this one, than the model where the magnetic angle is very high. Okay, and to improve the problem that they have seen into the convergence of the local solution, then they have tried to improve the objective function by defining some torque maximization and trace here. And they have also tried to reduce the number of constraints. Yeah. Here, this is the test model that they have used for that with the distribution of the Gaussian function. Here you can see the different solution, the different scatter plot of the different models. And here they have also reviewed some objective function with the constraint. And here, this is the new result of the obtention of the topology optimization. So here you have the stress versus the average torque. Yeah. Here you have the Pareto optimal solution. Here you have the target area. Here, here you also have, so after minimizing the log of the stress, so this is the log of the stress, and then you can see that here you have some point that are inside the target condition area. So here they have used the model with where the band angle is 130, and they are be able to confirm that the solution satisfy all the target condition that they defined before. Yeah. And into the summary, they have seen that the GEMAC topology analysis feature is very helpful, and it have been used to combine multi-field and centrifugal force analysis motor, and to solve also the issue with the high torque result cannot be obtained for the moment, and the maximization of the average torque and the measure of the stress I define as the objective function. Therefore, with that, they have been confirmed the improved effect. Yeah. For as future perspective, they will also find how they will also see how to run this by reducing some calculation time. Okay, that's it for Hitachi. Then I will go to the last one. It's about Denso. It's also about the topology optimization here. So I will not follow in detail the PPT. So I will just present, I will try to present the Denso automotive. So Denso automotive so Denso, it is some automotive company. So he have several business. Yeah. So he also produce some automotive components. So here you have the six core business of Denso. This is the automotive component that made by Denso. Hey, and here they have also here tried to show how the topology observation is used around the world. So you can see that before 1980, so the topology observation feature have been not use it. And today we see that the topology observation is very important. So it's very helpful when we want to design some component. Yeah. Here, this is the process that followed by Denso in order to make some topology optimization. So here they make some topology optimization based on the sensitivity solver of JMake. Yeah. And here you have here you have the two methods. So into JMake you have the density method, where we will try to optimize locally. You will try to use the sensitivity solver in order to optimize locally the design region of the motor. And here you have the advanced topology optimization solver of JMake. So it is the normalized Gaussian network where you will have more option to get a new shape of your motors model. So this is the two method of JMake this is the two method that you can use to make the topology operation into JMake. So Denso have tried to apply the density method into this new into this motor model, and also into some actuator here. So into the matrix circuit of the actuator. Okay, so so to reduce some losses, so to reduce some losses of the motors, so they have tried to investigate on the design, on the geometry, on the design of the stator. Yeah. So here you have some characteristics, some condition that they have used for the optimization. So here you have the design region. So the two is the design region here. So with the density method solver, they have seen that obtain favorable geometry proposal for both loss and torque by positioning cavity in the reverse rotation direction of the screw. So here you can see some iron loss distribution into the T of the stator, yeah, that they obtain. And here you have some comparison between the iron loss of the stator and rotor using the density method. Yeah. And here they have also tried to apply the advanced topology optimization in order to find the best T, the best T of the stator. So this is all the characteristic that they have used. So here they have plotted the scatter the scatter plot of the result between the iron loss and the torque. And here they have seen that the beta solution. So here the better solution here, it can be this one. And with the best solution, the loss can be reduced. We have 17% of reduction of the losses with the same torque. Yeah. This is also the same result of comparison of the iron loss between stator and the rotors. Here you have different distribution of the multiflux orders when using the advanced topology solver. Here you have with the existing geometry, and this is with the optimized geometry. Yeah. They have also make the same analysis using some injection system here. So they have focused on the melting circuit here. Here, this is some setting that they have defined into JMAC, and this is the result when using the density method of JMAC in order to optimize locally the iron. So here you can see some result. Yeah, and here this is the shape that the final shape that they obtain after observation. And here they also analyze the flux density distribution and also the automatic force produced into the core of the injection system. And they apply now the advanced method for more precision into for more advanced observation. So here you have the distribution of the Gaussian function. This is the result that they obtain. Yeah. And here you can see the result here, and here we make some comparison between the initial geometry here and the geometry obtained after making the operation with the Nginx solver here. And they have seen that with the advanced topology solver, so the Nginx method, they are able to derive the geometry that both improve electromagnetic force by reducing the cross section. Yeah. So this is another result that they display. So in the conclusion, they also said that this two optimization solver of JMAC, so the density method and the engineer method, is very, very helpful to find to explore the new topology of the motors. And here you have some summarize about the calculation time that they have used into these study cases. Okay, so do you have some question? Any question? Okay, so then we'll go to the second part about the automotive and the automotive application. So my colleague Ahmed will show you some presentation that some user have been done into this area during a user conference. Okay, so I will.
Okay, let me try to share my screen. Oh. Okay. Can you see my screen?
Yes, we can see your screen. Yeah, thank you.
Okay, then I will directly start. So this presentation is from Eisen Group, done by Mr. Masako Shibamori. The title is JMAG and GT Suite link for EV drive motor and 1D thermal analysis. Going through this presentation, I will be skipping also some parts, mainly. Yeah, you can just read this on the internet, even like the capital, the company profile. But let's go directly into the presentation. And first of all, the need to why do they need to do a thermal analysis for an e-axle motor? It is basically because of the increase in magnet temperature. And after a certain point, especially at this region, you can see that there could be some demagnetization occurring. So the main goal is to check the magnet temperature, the coil temperatures, and prevent the magnet from demagnetizing. So where are the main losses occurring? So if we check here the heat circuit of the motor, here you have the sinks, so which are the air and the oil, and you have mainly the magnet, the shaft, the core, the stator core, the coil, and the case. Also you have, so the magnet gets its losses from the magnetic eddy current losses, the rotor core from the rotor iron losses, same for the stator, and for the coil you have them coming from the copper losses. So, usually when designing the motor and calculating the thermal the temperature increase, this was done through an Excel file developed by Eisen. This has been done for the driving pattern. So here we have a driving pattern WLTC mode. So speed, time, the requirement, the torque. And usually what would happen is that you would calculate your magnetic field analysis using JMAG. You create a loss map using the copper losses and the iron losses, and then feed them into this Excel file where you do a thermal where you do the thermal calculation. This of course takes a large amount of time, and they were searching for a better solution. So quick introduction for GT Suite. So GT Suite is a multi-physics simulation tool that can run multiple multidisciplinary calculations such as 1D thermal analysis, electromagnetics. It has a direct link to JMAG, and this is what they took advantage of in this study. So why did they choose GT Suite? So as I said, direct link to JMAG RT, and the ability to create a 1D model from a 3D geometry for the thermal calculation. So here we're going to talk about the thermal analysis that were done. So as previously stated, so we have our loss calculation done in JMAG, where you have the rotation, speed, torque loss map. The conventional method was to calculate the temperature increase using Excel. But here, what they tried to use now was a faster validation using GT Suite, and also with the optimization tool Mode Frontier. This, of course, reduces man hours for heat evaluation because you don't have to input everything into Excel, and you can also consider the effect of material change. So if we check the analysis time per machine, we see that here for what you can do with 20 machines in GT Suite, the time needed for 20 in Excel can be done within one. It's a 20-to-1 ratio between Excel and GT Suite. So you just have to input the loss map of a signal magnet temperature only. So just a 2D lookup table here where you have rotation, speed, torque, and losses, and you can directly calculate the temperature increase. So if we look at the test bench that was applied here, so here they installed a magnet thermistor on each magnet, and for the coil they used a thermocouple inside of the slot and the coil end. So, and they did this on 3 evaluation points, which are the high load, short speed, high speed, low torque, and this is also a deeper point into the very high speed region. So if we check, if we compare the analysis to the actual measurements, we see that for case 1 we have a difference of up to 21%. Case 2 we have a difference of up to 15%, and case 3 of up to 34%. So what they did afterwards is they used the optimization tool Mode Frontier to try and correct for the thermal conductivity and improve and sort of do a curve fitting for minimum temperature difference between the 2 points. So if we check after the improvements, after the use of Mode Frontier, we see that for case 1, we have an improvement of, now the temperature difference is just 2%. For case 2, it's just 3%. However, for case 3, we see no major difference, and it is still at the 27% range. So we use this simulation afterwards to do it for a complete drive pattern. Or not we, like the customer used it afterwards for a complete drive pattern, and they checked coil temperature, comparing both analysis to the actual machine measurements, and we see a very high accuracy being achieved, in both cases for the whole drive cycle. Then they wanted to verify the loss map at each magnet temperature. So for different magnet temperatures, we see that for the continuous region here, we find that the error margin for copper loss and iron loss has a large effect on the temperature. And we see that analysis number 2, which is creating a loss map for each magnet temperature, gives the same trend as the actual machine. So the difference between analysis 1 and analysis 2 is basically in analysis 1, a single magnet temperature is being used, but for analysis 2, we're modifying the magnet temperature according to the losses. And we see this gives a much better, let's say, compliance to the actual measurements. So if we check this within a GT Suite, basically what would happen to modify for magnet temperatures is just instead of having a lookup, just a basic lookup 2D table, we will have a multi-dimensional table with all the characteristics, with several magnet characteristics. We see for case 3, which was our biggest, where we had our biggest error margin, is that the difference, the coil temperature difference drops from 27% to 11%. So much better accuracy is being achieved when accounting for several magnet temperatures. Then we go to 1D analysis 2, which is basically linking JMAG RT with GT Suite. So it's just a direct interface. You don't have any other modules, and you have a JMAG RT block, which can be directly implemented into GT Suite. The basic workflow of it is you create a GCF file, you create your RT file, you correct the RT file because the analysis is done with a sinusoidal current, and you make the correction accounting for harmonic content, and then you run the coupled analysis between JMAG RT and GT Suite. So the direct link between JMAG RT and GT Suite. So here you enter the copper losses to the coil, enter rotation losses to the iron core, and here enter stator iron losses to the stator core. And you have here your heat circuit calculations. And you get a feedback coil temperature and a feedback magnet temperature. And with the modified model here, you can basically account for all temperature dependencies. So here we can confirm that the motor output, so current, torques, and losses changes according to temperature feedback from GT Suite. So here is the rising coil temperature, here is the rising magnet temperature, but at the same time we see a decrease in torque and decrease in iron losses. Okay, skip this. So yeah, so basically what was achieved here is that you can account for, you can use the loss map created in JMAG to create an analysis model as a reference in GT Suite to accelerate the speed of thermal analysis. Of course, the issue now is to improve the accuracy of the thermal analysis model and the motor loss efficiency analysis. The second, in the thermal analysis 2, which links GT Suite to JMAG RT, they will add a control circuit model to attempt to analyze the control logic. Okay, that will be it. And then second presentation is motor loss calculation under PWM switching. Oh, sorry. This was done by Ji-Hong Kim from General Motors. So the key points here are motor loss calculations under PWM switching, and directly a conclusion. I will skip over the General Motor electric vehicles strategy. So going here, motor loss calculation under PWM switching. So background, so traction motors for eDrive are operated over variable speed and load. The variable frequency voltage source inverters are widely used in the eDrive. Harmonic content from current clipper results in additional motor losses, which contribute to the electric vehicle losses. And we see that there is a paramount need for accurate loss calculation, considering the PWM and the harmonic effects. Okay. Okay, I think I have an issue here. I will have to stop sharing for a moment and get back to you. One moment, please. I think we have a technical issue here. One moment and I will. Okay, I think there is. Okay, I can't find the correct one, so I'll just continue with this one here. So, sorry for this, I will continue. So, general factors to influence core losses. So from the magnetic aspect, there are 2D flux, anisotropy, DC bias, and mechanical and temperature dependencies. For the manufacturing process, there is, of course, punching, interlocking, welding, and press fitting. And of course, from the motor and inverter side, there are space harmonics and time harmonics. So what are the core loss calculation methods in JMAG? So first of all, we have, for eddy losses, we have an FFT method, which is post-processing. Then we have hysteresis loss, so hysteresis loop calculation. This is done by the apply loop method. The advantages is that it can accurately calculate harmonic components. Of course, this takes a bit more time, and of course you are bound by the limited availability of the frequency flux density core loss data, so the measurement data that you have. So another method to calculate core losses, which is a time domain method using loss coefficients. Okay. Using loss coefficients. Okay, wait, I think I have the final. This is not the final version of the document. I will download the final version now. Stop sharing again. One moment, please. Sorry. Okay, I have it now. Let me share my screen. Let me zoom in a bit. Yeah, so sorry for this. Again, going back to the presentation. As I mentioned, there is a second method other than the apply loop to calculate core losses, which is using the time domain method, where the loss coefficients Ke, Kh, and Kc are found by the least square method for all frequencies. This is a very fast approach. There are no post-processing. There's no post-processing required. However, there's introducing a lot of fitting errors for loss coefficients. And if you have a large di by dt, you can get some overshoots and overestimate your losses, as seen in the curve here, where the actual core loss is this range, but this method sort of, because of the large changes in currents due to the inverter and the large frequency changes, you see a huge spike every now and then. So setting this up in JMAG is quite easy, actually. So this is this is known as preset 1, which uses apply loop and FFT. You also you just have to specify the number of poles and the angular velocity. Other options which are needed is basically the sort of the flux loss frequency curve, and with it the losses are calculated. So for the circuit, what they used here was an external sort of a point sequence data, and from it they tried several types of current input. And for the AC copper loss calculation, you have a transit time analysis is required. So here we do a transit analysis of the copper losses, which is the allow eddy current option within JMAG. Additionally, for magnet losses, you also do the user also used a transit analysis, and the eddy currents were allowed, and the electric resistivity was set up. So there are two cases which were tried out here. The first one compares a sine wave drive to a PWM drive. The second one uses a sine wave drive compared to a 6-step drive. And core losses, copper losses, magnet losses, and total losses were compared in both cases. So for case one, which we see the PWM, we see very high harmonic orders in this range, which need to be taken into account during the simulation. For the 6th step, we have a bit less of low harmonic. We have a bit less of these harmonic orders, but which in the high frequency range, but in the low frequency range, we have some several components that need to be taken into account. This is just a basic FFT of the current drive. So here we see a calculation example comparing core losses from a sine wave drive, so 357 watt, to a PWM drive around 600 watts. Of course, we see a high elevation because there are much more higher frequency components that are caused by this PWM drive. Then we compare again for case two. We have for a sine wave drive around 760. For the 6th step, we have around 1,134. We compare both copper losses here. We see that it's around 40 watt for sine, 87 watt for case one, for PWM, sorry. And for the 6th step, we have 75 watt for the sine wave drive and around 400 watt for the 6th step. Similarly, for magnet losses, we have 1 watt for sine wave drive, and for PWM drive, we have around 76 watts. And for the 6th step, it goes from 3 watts to 135 watts. So here's a quick loss summary. They didn't compare. They weren't able in the test bench to separate the losses, but they have the total losses here. So here we're going to compare PWM drive, which is much closer to the actual measurement than the sine wave drive. And for the 6th step, we have actually very close or very agreeable result compared to the test data. Of course, the sine wave drive there is a bit of underestimation. So conclusions: PWM current ripples play a role in increasing motor loss significantly, so they have to be taken into account into the motor design. Magnet losses are mainly due to the PWM drive, and they should be considered appropriately. So additionally, system level optimization is required for including optimal switching strategy. For a better prediction of the PWM effect, you have to do an accurate current prediction, coupling with FEA calculation, time step, mesh quality, 2D versus 3D. All of this are factors that need to be taken into account. A better core loss model to capture complex magnetic behavior, good material magnetic property to support loss models. That would be it. Thank you. Okay, then let me move on. Let me stop sharing for a moment and go back.
Hello, okay.
Yeah, I'm waiting for the file to load. Sorry,
Okay.
I just there was an issue with the final version, so yeah, these are the final versions. So I would like to present from this. So the next presentation, let me zoom in a bit, is from Honda, which is with the title How to Leverage JMAG RT for Model-Based Design and its Prospects. This one's done by Mr. Shingo Soma. We're going to talk about, I'm going to skip the Honda initiatives. I'm going to be talking about model-based development and development examples utilizing RT and its prospects. So quickly here, let us start with model-based development. Let me zoom in a bit more. Okay, so the development cycle for model-based design first starts with setting which is the typical V shape, which is first setting performance objectives, a virtual confirmation of actual vehicle performance. Then you have part design, prototyping. Then you have individual test bench evaluation, combined bench evaluation, so you're considering several factors at the same time. And then you actually do the actual vehicle evaluation. This is, of course, a very long process. And with model-based design, you can actually skip, or not skip, but do several parts at the same time in order to save first time and prototyping costs. This will be done through mills, hills, softwares. So here in the mills, you're going to be interested in control. And you have a plant model such as JMAG RT, which can be used, and the same for the hills, which is the ECU build. You can focus this with JMAG RT. This can save cost up to several millions of labor hours and hardware. So on the vehicle level, we have the vehicle requirements and the actual vehicle compatibility verification. For the system level, we have the function requirements and the single unit compatibility verification. And then on the module level, we have the algorithm design and the implementation assurance. Here, Honda differentiates between the supplier and the manufacturer. So the supplier should give the algorithm design, the implementation assurance, and the single unit compatibility verification. Honda is responsible for function requirements and actual vehicle compatibility verification. So issues that occur in model-based design is basically you have to communicate between the motor hardware development and the motor control, ECU development, and inverter development. You have your interface with the JMAG RT, where you're basically comparing and adjusting ideas. So from the Honda side, they would, for example, give the environment construction supports for mills and hills. They give the motor specification design, the motor model, loss, and characteristics information. From this, this will be input into JMAG RT. This can be given then to the supplier, where estimates of the environment constructions can be made, controller design can be started, requirements analysis, control model creation, behavior consistency verification, and software shipment can then afterwards take place, which can be then from the Honda side verified with differences in CAA, which is basically just a current analysis comparison with conventional pre-built control. And basically it's let's say a communication channel between both the manufacturer and the supplier, where you have a single interface in the middle, which in this case is JMAG RT, and you're sort of communicating all of the motor design parameters and the control circuit parameters and the ECU development parameters, all within all using this interface. So development examples using JMAG RT. So for example, here in motor loss differences using PWM drive. So use of control systems with your JMAG RT models to combine them with FEA models. And this can be done directly within JMAG. And you can actually recreate current waveforms through the use of JMAG RT models. Additionally, you can use JMAG RT to reduce the time of the PWM simulations by first calculating using JMAG RT in the transient period, and then using the JMAG solver afterwards once you reach steady state. All of this can be done within JMAG Designer and JMAG RT. Additionally, you can accurately calculate efficiency maps with the coupling of control circuit development. So here we have a motor inverter circuit, and with it you can create an efficiency map. So here we compare actual measurements to CAE. So for torque, we have, it's just a 2 Nm difference. Same for current. Iron losses are fairly accurate, just a 200 watt difference. Here they have a separation of losses. For DC copper loss, it's also very accurate. And motor efficiency is almost perfect. And with this accurate modeling, you are saving all of this prototyping time in the end, all of this V shape. Instead of going through the typical motor design, you are just in the end saving all of this and doing all of these steps directly in parallel. So the use of JMAG control circuits to generate current waveforms and can calculate very accurate loss maps, as stated, within the 0.2% range. Another use is the use of insulating film and calculating the partial discharge voltage. And here, where we have a surge in the inverter, we can check the validity of the insulation film to ensure that there is no discharge occurring. Additionally, from the motor control viewpoint, discussions can be had with the suppliers without the need of sharing geometry information. So it's just an RTT file in the end, which can be directly given to the supplier, and all confidentiality is saved. This, of course, makes sharing data much easier. For suppliers providing units that even include control, the results of the investigations can be obtained at a high accuracy. There is a very high level of closeness in the responsiveness to the actual machines, which means that weak points in the control can be comprehended with ease. And then lastly, you can confirm the effect of the condenser capacities easily. So here we have a differentiation between the OEM side and the supplier side. So from the OEM side, they just input the pole pairs, the changing of number of turns. They use this just to confirm. They use this to confirm the controllability of the motor. And here the supplier can just implement different phase, can implement actual phase current waveforms with high current ripple over small current ripple, and different modulations can be then implemented. So JMAG RT makes it possible to improve the validation certainty of the proposal content. Here you see an example where, we have suppliers from different regions all over the world, and Honda can directly share its information with these suppliers. So now there are some factors to be taken into account, such as improved accuracy, what are the calculation losses, and what are the calculation costs, and what are the additional characteristics that need to be taken into account. So of course, to improve accuracy, you need to increase tolerance, you need to have a finer mesh. You can, of course, go into 3D RT models, but this, of course, goes into the calculation cost, where you have a large-scale model. Additionally, you can consider temperature characteristics, but this, of course, goes into the calculation cost. All of these are let's say, future possibilities that can be taken into account. So a quick summary. Using JMAG RT means that the conversion is possible without the need to present any motor geometries. Because the circuit editor is included in JMAG, motor designers can carry out highly accurate efficiency calculations. And when outsourcing the control, efficiency can be included in the required specifications. Required specifications for aspects of control are put together, resulting in an environment where both parties can confirm those aspects. And then lastly, it is further needed to improve JMAG RT accuracy through the use of 3D models, thus accelerating the development without the need of actual physical prototypes. That will be it for this presentation. Sorry, again, I'm going to have to stop sharing for a moment. Okay. So the next topic is reduction of optimal design time for IPMSM motors with machine learning. This was done by the University of Osaka. Presenter was Mr. Yuki Shimizu. So the contents here are the research background and objectives, the used machine learning methods, analyzing learning data using JMAG, learning machine predicting results, minimizing the amount of magnets. That is another optimization that is going to be run, and then a summary. So for automotive applications, when trying to run, when when trying to do an optimization, you have to do a driving characteristics at several speeds, at several current combinations, yeah. And you get different speed curve characteristics. Analyzing this using just using FEM can take a significant amount of time. So the idea here would be then to generate a random number of minimum motor shapes in advance, perform FEM analysis on these models, use these analysis models then to create a learning algorithm, which would then be used to generate a relationship between the geometry and the driving characteristics. From this, an optimization can be then run and using the surrogate model. So here is the flowchart of the algorithm. So first of all, you have your input, your required driving points, various restrictions, current restrictions, voltage restrictions, and some physical as well. You generate several current conditions, several models. From these, torque speed curves are being created. This is then fed into the learning algorithm, which is also being fed from the models that have been created for this optimization calculation. And the surrogate model is then being used to define the relationship between the geometry and the driving characteristic. And then it's just a feedback loop where if the optimization is completed, you go back, you generate more models for optimization. You then can directly, because you know the relationship between the geometry and the driving characteristics, you can just directly generate a torque speed curve and then check if you have reached your convergence criteria. So the research objective was to learn the relationship between the structure and the driving characteristics using machine learning. So the design of geometry optimization without the use of FEM, which is the main goal here, and to try to save a lot of time. And the presentation content shows that the geometry optimization can be performed within short periods of time without having to run several thousand cases using FEM. So here now we're going to talk about the use machine learning methods. So first of all, there's ridge regression. There's vectors, which is a type of linear regression analysis. Is quite basic. The error function of the least squared method usually includes the regularization term to suppress overlearning. Then you have support vector regression and XGBoost regression. Both are very noise robust. The second one is a type of gradient boosting. And this is basically, these learning algorithms are basically how the optimal solution is being found. So analyzing the learning data. So here is the motor that is being evaluated. Just 48 poles, 48 slots, 8 poles, distributed winding. Here are the features of the motor. So rotor diameter, air gap length, and the maximum terminal voltage. There's also a temperature condition set at 180 degrees. Then there were some geometry constraints being set up. And once these were set up, 400 geometries were being generated. Several phase currents were being tested at 134, 105, 75, 45, and 15 amperes. And then current phase angles were then being also combined with them. From this, around exactly 8,000 cases were generated. And this was sort of your learning data. Then this is just a basic parametric function to generate the geometries, and the FEM calculation was then being calculated. Then here, this is a state of generating structure in an animated form. I think, yeah, it's not working. Then learning machine learning prediction results, sorry. So the motor parameters were being calculated from these 8,000 cases. Rotor geometry was then you're calculating magnet flux, inductances in the DQ axis. And then these were then used to compute the torque speed curve, just using a quick analytical calculation here. And this is sort of your result from each FEM calculation, this torque speed curve. This would then be used in the machine learning algorithm to see which ones produce the best results. So the magnet flux by the permanent magnets, here you have the three learning algorithms. You have the REG, the SVR, and the XGBoost. This is for magnet flux, D and Q axis inductances. We see here for various characteristics that the magnet flux by the permanent magnets. The prediction accuracy, is that the SVR is the most accurate method in comparison with the other methods. The reason, for example, here the XGBoost learning data is discrete data, and the step width of the predicting characteristics is rather wide, just thus reducing the accuracy of this algorithm. Same also occurs for the DQ axis inductances. We see that the SVR is the most accurate method for both of them. We also see that the result here is quite stable and accurate across a wide range of speed torque regions, not just for the low speed high torque and the low torque high speed region. So for over the whole operating range, we see that the SVR here is quite accurate. The REG here, for example, is deviating up to 10%, and the XGBoost changes, keeps changing from positive to negative 10%. Then some motor parameters are better. Motor parameters are better at improving the prediction accuracy for the torque speed characteristics, of course. So predict motor parameters and compute speed torque characteristics. And then here use predict speed torque characteristics directly. If you use the motor parameters, you have a better prediction. Then a second optimization was being run, trying to minimize the amount of magnets. So the algorithm here is a bit different. So first of all, you generate a random number of initial population. You select the parents, you select the children. You correct the individual children with geometry constraints. You compute then the valuation values with the SVR. You select the best individuals, and then if the termination conditions are being satisfied, you finish. If not, you go back and repeat this. So in this case, the number of children was 88, the individuals was 253, and you had 11 design variables. And this evaluation was done with a fitness function here, which is the amount of magnets. It's done with the volume, actually. So amount of magnets and the amount of magnets for the conventional geometry that was taken as a base unit. And you had a penalty function. At the end, if here, the penalty function, if torque increases or decreases, so you have a torque range where the torque remains, and if it jumps above it or below it, it's a penalty function. A penalty is being applied. Additionally, if a certain geometry constraint is also broken, then another penalty is being applied. So this ensures that the geometry stays within a certain range and also the torque stays within a certain range. Just constraints of this algorithm here. So we see here that the computation time is reduced by almost 50 times. If we compare them, we see that the learning data analysis time is around 67 hours. The SVR learning time is about half an hour. And the optimization calculation time, which is without FEA, is done in 3 hours. So total computation time is around 72 hours. Doing this with just FEM analysis, you jump up to 3,000, almost 4,000 hours, so 4,000 computation hours. There is still a prediction error in the SVR, so it's not going to be 100% accurate. You see here, I'm going to compare quickly between the difference between the FEM analysis and the prediction value. So for current phase angle, you have a prediction error of 2%, 1% here in the magnet flux. D-axis is 0.4. There is quite a high error in the Q-axis, which is around 5%. Reluctance torque is also increased in the average torque. So because there is an error in the Q-axis, you get an error in the average torque in the end. Quickly, the cause of this prediction accuracy is that compared to conventional geometry, the best individuals are generated in a region that is low in data density, which then causes this error. And tendency then realized by this algorithm is that the geometry then overestimates the torque. So policies for increasing accuracy in the future using a Bayesian optimization, the curve will sort of be fitted. So here is the initial search where the application model here, and then you have a bit of error here. And with this optimization, you are doing some sort of curve fitting, which allows for all solutions to be taken into account. Then a quick summary. The torque speed characteristics were used. Torque speed characteristics were used as learning data, and from the design variable. Sorry, I messed up. Torque speed characteristics were being characteristic from the design data and the current vector inputs. The SVR learning method was found to be the best method, and computation time was reduced to about 1/50, so 50 times faster. Okay, that is it for this presentation. I think I have to hurry. We're running out of time. Stop sharing for a moment, and then I think I have one more presentation to be presented here. My final presentation is efficiency map generation and simulation of dual three-phase PMSM motors. This was done by Daniel Keller from Daimler. So the content, introduction of dual three-phase motors, machine model and design, simulation workflow, efficiency map case studies, and then conclusion and further steps. So some quick application of dual three-phase PMSM, which is just steering, hybrid motors, and traction motors. The reasons is that you have a decrease in current phase, so you have an increase in output power and lower torque pulsations. Number of phases is not only, and you can scale with the number of phases, but yeah. You have an asymmetrical dual three-phase PMSM here, where you have a 30 degrees phase shift, if you see the winding here. But you can also have a divided stator configuration where you have a 0 degrees phase shift between the three phases. And there is a significant behavior change between both methods. But what we're going to examine here is the asymmetrical dual three-phase winding configuration. So some test bench measurements were being done. And you can see here that at 2000 RPM, you have very, very low frequency current harmonics that are occurring. And these have to be taken into account at the very beginning, at the very early development stage. So just to model this is just a basic DQ axis conversion. So here are the ID IQ values for the first three-phase combination, and then for the second. And this was done just with a basic Parks transformation. Then you have here the voltage equations. So the voltage level D, Q, D, Q. And you can accurately model this using a lump parameter model. So the design process of the dual three-phase PMSM, you first try it in the initial winding design, then you do an FE simulation optimization, then you move on to the control and system simulation. So for winding design, you have a very basic design in JMAG Designer, which can help this. Crossable within JMAG Express and also JMAG Designer. JMAG now supports the possibility of creating speed priority efficiency maps using 6-phase PMSMs. Also, you can consider differential inductances in the DQ axis. And this is a very fast method to evaluate the motor. Then you can consider current harmonics. Also within JMAG Designer, this is done through either, so if you do a current-driven finite element simulation, you don't have a transient effect in the beginning, and this of course saves you a bit of time. But if you do it with a voltage source, then you have this, then you can consider current harmonics. And these low frequency current harmonics are needed to be taken into account. Then within JMAG Designer also you can implement a feed-forward control, the flux of the coils, to generate this controlled voltage-driven simulation without any prior knowledge. Then using speed mode accuracy, then you can generate an efficiency map with this control circuit and this using the accuracy priority mode accuracy priority mode efficiency map. And there you can investigate different machine topologies and also the control circuit, the current harmonic dynamics. Additionally, you can calculate the efficiencies at the drive cycle points. So here is an efficiency map, and here are the drive cycle points, so the WLTC points, and you can calculate the efficiency at each of these points. Then we move on to system simulation with JMAG RT. there is a possibility to implement control algorithms with JMAG RT, and also you can test system faults. So model-based design increases the efficiency of the development process and helps shorten the development cycle. So lastly, simulation of dual three-phase machines, including the winding design and efficiency map generation, is supported by JMAG. The dual three-phase permanent magnet synchronous machine creates this low frequency current harmonics which need to be taken into account. And then for further steps, the development and measurements for further rotor designs to reduce current harmonics, and development of a characterization method to determine feed-forward control and PI controller gains at the test bench. Thank you. I think I am done for my part. My colleague Yves will continue with the final two presentations.
Okay. Okay, thank you, Ahmed. Maybe you can make Yves
I can make the host.
Yes. Yeah.
Make host.
Okay, thank you, Ahmed. Can you hear me well and see my screen?
Yes.
Yeah, thank you. So only 5 minutes is remaining. Fortunately, I have two presentations, not so much, so I will try to make it efficient. First one, so those two presentations is now dealing with, let's say, aerospace domain. So the first one is from the JAXA, Japan Aerospace Exploration Agency. And so from the abstract, we can see that this is mainly dealing with temperature and thermal design using JMAG-RT and AMESIM software, which is a 1D multiphysics software. And JMAG-RT could be included in some, so the behavior table from JMAG-RT could be included in the AMESIM table. So this presentation has been given by Mitsuru Shimagaki. So here is the device. So this the motor that we are going to investigate is a motor for turbo pump for propellant supply for rocket engines. So here is the turbo pump here, and then you can see in more details here the motor. Here is the motor, so you can see this part. This part is the motor, and then here you've got the pump. Okay, and so many issues occurred in this motor. So vacuum electrical discharge, motor heat generation, and cooling heat balance, and also rotor vibrations. So what are the results in 2019? So the previous results and the investigation of the previous calculation was about the vibration and especially the eccentricity and the resulting forces. Due to the eccentricity, due to the fluid that will flow into the impeller. So this is the kind of eccentricity that can be seen here, and the kind of torque and torque ripple. Okay, then we also switch to the equivalent thermal circuit. this what has been so down here, and so some temperature has been calculated. So here you can see that cold stator gap magnet has been created, yeah, the corresponding thermal equivalent circuit has been made. So what are now the new objective? So in 2020, the objective is now dealing with issue number 2, which is the motor heat generation and cooling heat balance. So first, this is the motor specification. Here, this has been calculated by JMAG. Motor output 90 kilowatt. This is a rated rotation speed. Motor type, surface type magnet, permanent magnet, synchronous motor, SPM. And then this is the analysis preparation, and especially the platform preparation. So this is what you can do in AMESIM. So you can, AMESIM is a 1D multi-domain simulation software. So it means you can simulate, take into account the fuel, the impeller, and all interaction, and then also take into account the motor. And this motor will be, so the behavior of the motor will be coming from the JMAG RT, so the behavior table from JMAG RT. So here you can see the JMAG RT input information. So this could be specified in AMESIM. Okay, so you can specify that this is a spatial harmonic model that is taken into account, that has been used. Okay, then you need to specify where is the DLL and there is the RTT file. And then also, as you may know, that RT is a quasi-static calculation, so no AC losses are taken into account. But here, making some additional calculation to reflect the effect of the AC losses into the RT model has been done. So some fewer or additional simulation calculation with JMAG, and only JMAG has been made for take into account those AC losses and to reflect that into the resistance of the RT model. So then you can see the results. So on the left-hand side, you can see the ideal model or AMESIM model, and then on the right-hand side, you can see the AMESIM using JMAG RT. And then you can compare the core copper loss. Okay, so you can see that with the improved resistance, you can see that the loss are bigger. Okay, and you can also see that with JMAG RT here, you can also see the current, which is also bigger, and then the results. You can see the consequence into the temperature. So here you can see the temperature at the rated speed. So then temperature taken into account the AC losses is of course higher, and so the user has been able to update and to design his cooling device. Here you can see the observation that, of course, calculation time is longer with JMAG RT because you need to generate this RT table, but then you get better accuracy. Yeah, so thank you. It's all for this one. So I will switch to the next one. Next one is from Mitsubishi, and it has been presented by Hiroshi Mitsuda. This one is dealing with electric hybrid electrical propulsion for aircraft, international air transportation. Here, the main issue will be, in fact, to check, of course, efficiency, but also power factor, so that the weight versus output power is the best ratio. And here we will see that PSL, Power Simulation License, has been used. So maybe I will skip the background. So just to summarize that the tendency is the trend is more now dealing with some electrical propulsion for let's say a kind of hybrid propulsion, hybrid motor. And here an important topic for aircraft motor, electrical motor in aircraft is of course the efficiency, but you can see that also power factor will be a big issue, because it will affect the weight of the electrical equipment and especially the weight of the motor. So you absolutely need to check your power factor and to optimize your power factor so that you can reduce the weight or increase the weight output density. So three different types of shape has been investigated here: inner rotor, outer motor, and double rotor. Okay, and all those three topics will be investigated, but the main important one is the power factor. So efficiency map will be outputted. So PSL, Power Simulation License, for running a huge amount of quantity of calculation will be used. Two test environment will be done. You can see that total number of CPUs are identical, but here it's onto one single computer, and here it's using several different computers. This is the design procedure. First, speed priority mode for getting efficiency map will be done with several iterations, checking that specification has been met, weight has been made, and etc. Once it is okay, some accuracy priority mode will be made, and final step will be kind of 3D calculation for checking eddy current in the magnet. So let's check first the speed priority. So once again, here is the 3 different devices with the motor specifications. Here is the different result for the speed priority mode. So you can see that efficiency is more or less nearly identical, but you can see that with the double rotor, the power factor is quite better. So maybe highest power factor will be reached with the double rotor. Okay, here you can indeed see that inductance is quite low with the double rotor. So then the power factor is of course better. Okay, sorry, I have a kind of display issue with the PDF here. This is a kind of summary. So you can see that the weight output density with the double rotor, we are better. For non-electrical part, maybe that's identical between inner rotor and outer rotor. And this one, I don't remember what it is exactly. Anyway, that may be the total efficiency or something like that. Then let's switch to the accuracy priority. Okay, and so 3D calculation has been made, so that you can see that the magnet is segmented and some insulation has been placed. Okay, and you can see the different efficiency map here. Okay, so this is for eddy current verification, taken into account eddy current in the map. And then we can also use, in the accuracy priority mode, we can also use the drive control using PWM. So you can see an example of current with all the harmonics due to the PWM, due to the slot ripple. And then this is the loss analysis results comparison. So here is the results from the speed priority and accuracy priority mode. So you can see that the efficiency of the double rotor is around 94%. Okay. Here you can also see the resulting calculation time. So using the PSL. So you can see that using several computer is a bit quicker for the accuracy priority mode. And then you can see that for the double rotor motor prototype, the weight has been achieved. The weight output density has been achieved, and the comparison between the calculated values and the measured value. So here you can see that some cooling part, let's say the non-magnetic part, has been also added, and you can see that this is matching very well the measured value. And yeah, you can also see that the power factor is quite good for the double rotor. Efficiency is nearly same, and so of course the weight output density is better with the double rotor. So thank you very much for your attention. So we are nearly 10 minutes late. Sorry for that. I hope you've got a good overview of what has been presented in the user conference in Japan in 2020. Please feel free to go to the GMAG website. You will find all those user GMAG conference proceeding. If you go to technical libraries, and then here in the GMAG user proceeding, and you will be able to download and to check all the presentation available. So feel free to download, to check, and do not hesitate to be back to us if you've got any questions. So thank you very much. Didier or Ahmed, do you have anything to add?
No, I think everything is clear from my side.
Okay. Okay, thank you very much. So we can close this session. Thanks again for